Imagine you're at a party. Dozens of people are talking at once, yet you can focus on just one voice. How does a computer pull off the same trick with words? We're about to crack that mystery. We just faced the cocktail party puzzle. The solution is attention, a smart filter that scans all voices, picks the relevant ones, and blends them into a clear signal. The word attention comes from the Latin attendere, meaning to stretch toward. It's not just seeing everything, it's actively reaching out and focusing on what matters. We just saw attention as smart filtering. But why is it needed? A basic network reads every word with equal weight. In a long sentence, the key connection gets buried in noise, and the meaning becomes a blur. Attention fixes this by physically boosting the volume on the few words that matter right now, and quieting the rest. It turns a muddy mix into a clear, focused signal. We just saw how a long sentence becomes a blur. Now, imagine reading with a highlighter. You mark only the words that carry the core meaning. That is exactly what attention does. Think of a person reading a complex sentence. They scan all the words, decide which ones are crucial, like Kati and Isat, and mentally highlight them to grasp the scene. Attention works the same way, but mathematically. So, attention is a smart filter. It looks at every word in a sequence, calculates an important score for each, and then uses those scores to build a focused, context-rich understanding, just like your brain does when you read. We just saw how attention highlights important words. But a computer can't read words, it needs numbers. So our first step is turning a sentence into a list of numbers. We split the sentence into pieces called tokens, each is a word or even a part of a word. The word a playing might become two tokens, play and a thing. This keeps our vocabulary, our dictionary of known tokens, manageable. Every token in our vocabulary gets a unique number, like an address. So our sentence becomes a sequence of numbers, for example, 45, 102, 78. Now the attention mechanism has something it can work with. We just broke our sentence into tokens. But a computer can't do math on the word cat. So we translate each token into a vector, a simple list of numbers. Imagine a simple 2D space. Each number in the vector is a coordinate. Words with similar meanings, like king and a queen, end up as neighbors. Car is way over there. Real vectors use hundreds of dimensions, not just two. Each dimension captures a hidden feature of the word. This whole map from token to vector is the embedding. We just gave each token a single embedding vector. Now, attention splits that one vector into three specialized vectors, a query, a key, and a value, each with a distinct job. Think of a library. Your query is the topic you ask about. Each book has a key, its index card summarizing what's inside. The value is the actual book content you take home. A token's query searches through every other token's key. When they match well, that token's value is what gets highlighted and passed forward, separating what I want from what I have from what I give. We have one embedding vector for cat. To create its query, key, and value, we don't just copy it. We project it into three different spaces using three unique weight matrices. Think of a weight matrix as a set of knobs. Multiplying the embedding by it mixes its numbers, scaling some and combining others. This projects the original vector into a new space, like shining a light from a new angle to see a different shadow. We use three separate matrices, WQ, WK, and WV. Each one is trained to ask a different question of the embedding. WQ creates the search vector, WK creates the match vector, and WV creates the actual content a vector to be weighted and passed on. We just created our query and key vectors. Now we measure how well they match using a dot product. It checks if two arrows point the same way. We multiply the first numbers together, then the second, and add them. The result is our attention score, a single number that says how relevant this key is to our query. We repeat this for every key in the sentence. The scores form a heat map. Bright spots show which words our query should pay attention to. We just computed dot product scores, but they're all over the place, some big, some small, even negative. Without a shared scale, we can't easily compare which token truly matters most. Softmax first applies the exponential function, turning every score positive, with bigger scores growing much faster. Then it divides each by the total, so all weights add up to exactly 1, like slices of a pie. If scores get too large, softmax becomes extreme, one token hogs all the attention. We scale scores down by the square root of the key dimension, keeping the distribution smoother so the model can still learn from other tokens. We just turn scores into weights that sum to 1. Now, we multiply each value vector by its weight and add them all up. This weighted sum is the new, context-aware representation for our token. Tokens with high weights pour more of their value into the sum. Irrelevant tokens, with near zero weights, contribute almost nothing. The result is a blend where the most relevant information dominates. This weighted sum is the heart of attention. Every token in the sequence performs this same operation, gathering information from all others based on learned relevance. The output is a sequence where each token now understands its context. We just built a context-aware representation using a weighted sum. Now, what if the query, key, and value all come from the same sequence? That is self-attention. The sentence looks inward. Take the sentence, "The bank sits by the river." Each word becomes a query, a key, and a value. The query for bank looks at every key, including the key for river, to see what matters. The word bank is ambiguous. But after self-attention, its output vector is a weighted mix of all words. Because river gets a high score, the final representation leans heavily toward the land beside water meaning. We just built self-attention. But one attention pass captures only one flavor of relationship, maybe grammar, maybe meaning, but not both at once. To truly understand language, we need many perspectives in parallel. So we run several attention operations in parallel, each with its own query, key, and value matrices. These are called heads, and each head learns to focus on a different aspect of the sequence. Each head produces its own context-aware vector. We concatenate them, simply stack them end to end, creating one long vector that blends syntax, meaning, position, and more into a single rich representation. We just gave the model many heads to see different perspectives. But for predicting the next word, looking at future words is cheating. The model must only see what came before. Before softmax, we lay down a mask, a triangle of negative infinity over future positions. When exponentiated, negative infinity becomes 0, so those tokens get no weight at all. The result is a lower triangular attention pattern. The first token sees only itself, the third sees the first three. The dark upper triangle is the future, hidden, silent, unable to influence the present. We just masked the future. Now, that multi-head attention becomes one piece of a larger processing unit called a transformer block, a machine that refines each token's meaning step by step. First, a skip connection adds the original input vectors back to the attention output, like keeping a copy of your first draft. Then, layer normalization scales everything to a stable range, preventing numbers from exploding. After normalizing, each token's vector passes through a feed-forward network, the same small brain applied to every position independently. It expands the vector, applies a non-linear activation, then compresses it back, learning complex patterns. A second add and norm wraps up the feed-forward step. This full block, attention, add and norm, feed-forward, add and norm, is one complete refinement cycle. Transformers stack dozens of these blocks, each making the representations richer. We just built a single transformer block. Now, for translation, we use two stacks. The encoder reads the French sentence. The decoder's queries look back at the encoder's keys, creating a cross-lingual bridge. A chatbot like GPT uses the masked self-attention we just learned. When predicting the next word, the mask ensures it never peeks at the answer, forcing it to learn from context alone. For images, we chop the picture into a grid of patches. Each patch becomes a token, just like a word. Self-attention then lets every patch look at every other patch to understand the whole scene. We just saw attention-powered translation and chatbots. Now let's trace the full path, from raw tokens to a context-aware word, all driven by dynamic relevance. The query asks what's relevant. The dot product with each key gives a raw score. Softmax turns those into a clean probability distribution, weights that sum to 1. Then we blend the values accordingly. A single head gives one perspective. Multi-head attention runs this in parallel, 8 different QKAV sets, then concatenates the results. That feeds into a transformer block with a skip connection and feed-forward network for deeper refinement. Let's return to our cocktail party puzzle. We'll give the computer the noisy sentence "the cat sat on the mat" and watch it focus on the word cat using real numbers. The query for cat asks, who's relevant to me? A dot product with every key gives raw attention scores. The score with itself is a strong 9.2, while unrelated words like son score a low 0.3. After softmax, the scores become a probability distribution. The weight for cat dominates at 0.97, creating a sharp spotlight. The other words fade into the background, just like at a party. We just saw attention in action. The most common pitfall is skipping the scaling factor. Without dividing by square root d, large dot products push softmax into extreme values, killing learning. To never mix them up, think of a library. Your query is what you're looking for. Keys are the titles you match against. Values are the actual books you pull and read from. Grab a short sentence